Hello and welcome. My name is Noah Deere. Today we're going to do Lesson 2, Derivatives and Integrals of Vector Functions. And what we're going to do to start is we're going to look at what it even means to take a derivative of a vector-valued function and how that will give us tangent vectors. We'll see a little bit of background on how we subtract vectors in the first place. We're then going to look at building the functions for the tangent lines of a vector-valued function at a specific point. We'll look at how we then can normalize those tangent vectors to create unit vectors. And then we will look at, as some additional topics, some angles of intersections. If we have a space curve and another space curve that intersect, then we can look at what angle they actually intersect at. The next thing we'll look at is some derivative formulas for, say, we have a dot product or a cross product, and we want to be able to come up with the derivative for that when we have two separate vector-valued functions. We can come up with those formulas, and then we'll look at how to integrate some vector-valued functions as well at the end. All right, so let's get to it. I'll scroll down here. This intro is just talking a little bit about how derivatives of vector-valued functions have a correspondence to derivatives of single variable functions, where the derivative is going to give us the direction of the tangent line. Integrals of vector-valued functions are a little bit more abstract. They are not going to give us an area under a curve per se, but we'll look at some applications of that in later sections. So to get going here, what we want to do is remind ourselves that the derivative of a function is going to be given by the limit as the change in the input goes to 0 of the change in the output over the change in the input. So oftentimes in calculus we use h to represent this change in the input. So the whole reason that we're using the instantaneous rate of change where we're taking the limit is if we have a vector-valued function, r of t here, and we draw a vector initially for some time value, so here's r of t for some specific t value, and then we add some time so that we see we've traveled to this point along our space curve. And so here we have r of t plus some h. Then taking the difference between these and dividing by our change in time will give us this secant vector between these two here. But if we let h go to 0, then we're going to get the tangent vector at this location right here. So we let our change in time, or our h value, go to 0, and that should give us the direction of the tangent vector at this point right here. Keep doing that. Okay. So we see here the formula for our derivative as the limit as h goes to 0 of r of t plus h minus r of t. The subtraction being in this direction, we can see from this bit over here, if we remember how to do subtraction of vectors, I have a vector u along here, I have a vector v along here, and then if I go from u to the end of v, that should be v minus u. To check that we've put this vector in the right direction, add these together, right? Because it's nice to add u plus v minus u, and then I say, oh yeah, the u plus the negative u will cancel and we'll get the vector v. So that should be the order that, or the direction that we put our v minus u vector, and that's how we are going to see that we have r of t plus h right here minus r of t over the change in time, our h value down here, and that gives us our derivative. Okay, so we're going to now use this idea, but we're actually going to, in practice, instead of taking this limit over and over again, we know our derivative rules, and so for when we're actually taking the derivative of our vector-valued function, we're just going to take the derivative of each component individually. So, for example, right here, I want to find the derivative of the vector-valued function r of t equals cosine of 3t comma t, comma sine of 3t. So r prime of t equals the derivative with respect to time of our vector valued function and to do that we simply take the derivative of each of the components individually. So let me write this out here. Oops. And so then we apply our basic derivative rules for the derivative of a cosine of 3t. Here we need to use chain rule. So the derivative of cosine is negative sine. And we need to multiply by the derivative of 3t, which is 3. The derivative of t is just 1. The derivative of sine of 3t, again we use chain rule, so I get cosine of 3t times 3. And then I will just simplify this real quick. So I'll get negative 3 sine of 3t, 1, 3 cosine of 3t. Now, if we want to think about why we're able to do this component by component, what we really want to realize is the following. Say I have a change in r, and I recognize that this equals the change in x, the change in y, and the change in z, right? If we're going to change r, then our x value, our y value, and our z value are all changing, so we can assign some change in all of those. So then our change in r, my hand is doing that. So our change in r over our change in time equals our change in x over our change in time, our change in y over our change in time, and our change in z over our change in time. So when we're taking our derivative and take the limit as change in time goes to 0, that just gives us the derivatives of each of the components individually. All right, so that's an example of how we quickly just take the derivative of a vector valued function. Now go ahead and scroll down to the next page. And here, so what we want to do for this example is if I'm looking at r of t equals cosine of 3t, t sine of 3t, which is the exact example that we looked at before, can we find the tangent vector at a specific t value? So let's just copy down what our derivative function looked like. That was negative 3 sine of 3t, 1, 3 cosine of 3t. And all I really need to do to find our tangent vector is plug in our t value into our derivative function. That should give us a vector that points in the direction of the function at that specific point in time. So I'll plug this in here, sine of 3 pi, 1, 3 cosine of 3 pi. And let's just do some quick trig review. Sine of 3 pi, remember 3 pi is here, so the sine value is 0. So negative 3 times 0 is 0. 1, 3 cosine of 3 pi, that's negative 1. The cosine is the x value here, so we get negative 3. So if I were to graph this vector valued function and then look at the point where t equals pi, then the direction of the vector valued function at that point would be this direction right here. Now let's keep in mind from this definition here that a tangent vector exists at a specific point so long as the derivative isn't 0 and that the derivative exists. So the fact that the derivative needs to exist is kind of apparent. Like the derivative wouldn't exist if we had a sharp point or some sort of asymptotic behavior in our space curve. If the derivative equals 0, right, so if we plug in our t value into our derivative and we get a 0 vector, that means there's no movement, that the space curve is suddenly stopped, right? If we think of t as time, that means that there is no direction because it's like at that point time is continuing on, but the movement of our space curve is now 0. Okay, so we are plugging right along here, and we now want to take what we have looked at and we want to come up with the equation of a tangent line for a specific function. Okay, so what we want to do to start is we just want to plot this vector valued function. There's a lot more instructions here, but the first thing says sketch the plane curve. So let's just do that, get it out of the way before we worry about anything else that's going on here. So I'm going to go ahead and make a table of values. Whoops. Here we go. So I have t value, and then I want my r of t value. I am going to notice that we want r of -2, r of -1, r of 0. So I'm going to start at -2 on my table. -1, 0, 1, and 2. Just some nice t values. I'm also thinking about the following when I'm choosing these t values, is that this t squared plus 1 is a parabola whose vertex is 0. So having t values from -2 to 2 should hopefully get us to be kind of around some sort of vertex for our vector valued function here. So here, r of t, if I plug in -2, I get -4 for my x value, and -2 squared plus 1 is going to give me 5. If I plug in -1, I get -1 minus 2 is -3. -1 squared plus 1 is 2. Plugging in 0, we get -2, 1. Plugging in 1, we get -1, 2. And plugging in 2, we get 0, 5. And if you need to pause the video real quick to just catch up and make sure that you're getting all those calculations right, I'm going to go ahead and start plotting the position vectors. It says here in the instructions, sketch the position vectors for r of -2, r of -1, and r of 0. So r of -2 I see is -4. Let's get some scale on our axes here. 1, 2, 3, 4, 5. So we're looking at this point. See if I can get a steady hand here. And here is r of -2. r of -1 is -3, 2. This point here. So we're going to get this vector. And I want to be careful where I'm putting things. This is r of -1. And r of 0 is -2, 1 right here. This is r of 0. And then we have -1, 2. And then we'll have 0, 5. I'm not going to draw the vectors, but we're looking at these 2 points. So I'll go ahead and draw our curve that looks like a parabola here. So go through these points, and we will keep in mind the direction of this space curve is going this way. So if we're looking at this point here, we want the tangent vector r prime of -1. So the tangent vector here should be going in the down and to the right direction. To do this, let's start by finding our derivative function r prime of t. So the derivative of t minus 2 is 1, and the derivative of t squared plus 1 is 2t. So r prime of -2 equals 1 negative. Wait, what am I doing? R prime of -1 is what we want. R prime of -1 is still 1 here, and -1 times 2 is -2. So if we're creating our tangent vector, we want to actually put it from this initial point, right? So from our point, negative 3, 2, we go down 2 over 1. So this vector here, this is r prime of negative 1. Okay? And the reason we're going over 1 down 2 is because that's what our derivative tells us. It tells us change in x is 1, and the change in y is negative 2. So the last thing that we want to do is determine the equation of the tangent line at this point here. So if we draw it in, we see that we should keep this slope up, right? So we should be going down 2 over 1 over and over again. So we can draw it in before knowing its equation, and we can find its equation in a couple of different ways. So if I'm doing this, since I'm in R2, I could say, okay, here my y-intercept is 0, negative 4, and I'm getting that just by extrapolation. I have negative 1, negative 2, negative 3, negative 4, since this keeps going down 2. And this allows me to see that we have y equals negative 2 is my slope, x minus 4. So that's one way of seeing in 2 dimensions that our tangent line is this formula here. But we want to do this using vectors. So if I'm remembering how we find the equation of a line for vectors, we do this by saying that our tangent line, and I'm going to use a subscript r of negative 1. So I'm not finding the tangent line for some point like this one or this one. I'm finding it specifically at this location r of negative 1. So the tangent line here is going to be some initial point, which we know an initial point is r of negative 1, plus a scalar of our tangent vector. So I'm going to actually write this as r prime of negative 1. This gives us our general form for the tangent line at some point on a space curve r is going to be r of a plus t times r prime of a. T in this case is our scalar that is multiplying by this. Our r prime, this is kind of like our slope. If we compare this to our tangent line of a single variable function, so if I have a tangent line of a function at some x value a, this is going to equal f prime of a times x plus f of, actually, sorry, I need to back up just a hair, times x minus a plus f of a. So this is, the derivative gives us the slope, and then this is using the point slope form of an equation of a line. And here we can see that this is actually a little bit reminiscent of this. Here we have our derivative times our variable plus some point on the space curve itself. So we'll finish this up real quick by just going ahead and saying r of negative 1 is 1 comma negative 2 plus t times, oh, and I'm doing it again, r of negative 1 is, well, negative 3, 2, and the derivative is 1, negative 2. I was getting it backwards there for a second. Okay, and so we can leave it like that. Another acceptable form is to kind of put this all together, negative 3 plus t, comma, 2 minus 2t. And as an instructor, I am fine with both of these forms. Your instructor may prefer one over the other, but there's not a whole lot of difference other than just a basic form here. All right. So go ahead and pause, rewind, look at that a little bit if you have anything that you need to review. And once you feel comfortable with this process, go ahead and scroll down here. And what we're going to have you do is I actually want you to try this on your own. Pause the video and try this on your own. I'm not going to walk you through it. I just want you to go ahead and do this now, since you've just had me do an example for you. And then what I'm going to do is just give a little time, and I'm going to do it while the video is paused, and you'll just see the solution. I'll run through it really quick in a second. All right. Okay, so a few minutes has gone by in my time, but for you, this magically just appeared the solution here. So let's just run through this. I have plugged in t-values into my function to come up with my vectors for my space curve. So I've drawn r of 1, r of 2, r of 3. I've connected my points to get my space curve r of t here. And then we've taken the derivative, and I've plugged in the value 2 for t to get r prime of 2 is 1 comma square root of 2 over 4, which is not the greatest number, but I'm noticing that my change in x is 1, and I know that my direction should be here. So if I just draw it 1 unit over in the direction it should be, then I get my r prime of 2 vector without actually having to compute this value. I can then get the equation of my tangent line at r of 2 by saying what is r of 2 plus t times r prime of 2. So I plug those in and then go ahead and just simplify it down into a single vector form, and we're good. And my colleagues will kill me if I don't fix this on the previous problem, but note here I'm actually labeling my space curve r of t, and I'm labeling my tangent. So I'm going to go back up here and make sure that I've done that on this one as well. So here I have r of t, and this is t. So vector function t r of -1 of t. Okay, so I fixed that, and that is general good practice to be labeling your functions on graphs that you create. All right, back down here, and we will look now at the next example where we are going to use technology to plot these and create the tangent lines and all of that. So what we're going to do is we're going to open up Geogebra, and I'm going to do all of this in Geogebra, and here are some written directions so you can follow along on your own paper by reading these if you would like to, but I'm going to pretty much wing this. I'm going to open up my web browser here. So this is going to change your view. You're going to see some of my stuff here, but if we go to geogebra.org, then we can click on 3D graphing. I'll close this and redo it. And we'll get our fields here that we can plug things in. I'm going to close this keyboard. You're welcome to use it here if you'd like, but I'm just going to use the keyboard, actual physical keyboard, to do this. So I want to create an object r of t equaling a space curve. So I'm going to type in curve, and then the first thing I'm going to do is type in the expressions for the x, y, and z components of that curve. So I can type 4 square root of t, and let's try this again, 4 times the square root of, there we go. Now it's recognizing it. It wanted me to put that times in there, comma, t squared. And I want to plot this curve where the input variable is t, and we want to start this at, say, t is 0, which is the initial value of my domain actually for the space curve, and let's go to, say, 9. And here we get a picture of our space curve. Yeah, so that looked okay. So while I'm here, I'm going to go ahead, and if we remember that we now want to look at the equation of the tangent line at the point 4, 1, 1. So I've put in my space curve. I now want to put this point on there so I can see that. See if I can get this working a little faster. So I'll say the point A equals 4, 1, 1. And we get our point on here. Twist this way so I can see it a little bit nicer. I can hit the shift key and change my scaling in individual directions here on these axes. So I kind of like that for now. I can always move it later. And then if we want the tangent line plotted on here and then to get the equation of the tangent line, let's do a little bit of work on the paper itself real quick. So over here, I want now the derivative and that's going to give us, if I take the derivative here, I get 1/2 times 4 is 2 times t to the negative 1/2, or over the square root of t. And then derivative of t is 1. The derivative of t squared is 2t. And we want the derivative at this point. So if I have the point 4, 1, 1, 1, then we need to find what our t value is. In this case, it can be apparent by just looking at it. If you look at that for a second, hopefully you can see that our t value should be 1. We can also do this a little bit more systematically. So I can see that the first component has to be 4, so I get 4 equals 4 square root of t. So this gives me 1 equals the square root of t, so t has to equal 1, and then we can confirm that in here and make sure that that works. Sometimes we can get more than one option, and we could also make a mistake. So we just want to check that if I plug in 1 into these two components, we do in fact get 1 and 1 here. So we get a t value of 1. So we want the derivative when t is 1 for this function. So r prime of 1 equals, this is nice, I can take the square root of that, get 2, 1, 2. So that's the direction of my tangent vector that we want to plot. So let's go ahead and do that real quick, and then we'll come back and we'll get the equation of the tangent line in a second, which is just going to be analogous to what we did in 2 dimensions, but we'll just get to see that in 3 now. So over here, I now want a vector, I'm going to call it a vector, let's call it t, equals vector, and we want a start point and an end point. We don't, if I just put in the vector that we just saw there, 2, 1, 2, notice that it's starting us out from the origin, which is not exactly what we want. What we want is we want to start from A, and now it's still not going in the right direction. So we realize that we want it to go from A to A plus the direction vector, right? So that we've now gone from A, and then we've moved in the direction of 2, 1, 2. So that means that this vector is actually A plus 2, 1, 2. Gives us this vector here. Okay. And we can actually change our view and see that, yes, that looks like the direction vector that we want for our space curve in this location. Now, let's go ahead and get the equation of the tangent line real quick. And so back over here, sure, I'll switch colors. Remember, our tangent line at a specific value is going to be a point on the tangent line, which is nice just to take the point from that vector function that we're looking at, plus t times r prime at that t value of 1 here. And so we get r of 1 is, if I plug in 1 here, I get 4, 1, 1, plus t times 2, 1, 2 equals 4 plus 2t 1 plus t and 1 plus 2t. Anyway, 4 plus 2t, 1 plus t, and 1 plus 2t. Okay, so I'm going to take this and put this in as my next vector valued function. So I'm going to go here, and I can actually label it this. So I can say t sub r of 1, and I'm just using that subscript to indicate that that's the specific tangent line that we're looking at. T of t equals, we want a curve, and the first thing I'm going to do is plug in that 4 plus 2t, and then we have 1 plus t, and then we have 1 plus 2t, and we want to that curve in terms of t, and let's just go from 0 to 4, say. I'm just guesstimating here and see if it works. We can adjust our input values if they're not clearly visible here. So we see that at 0 we're getting a, which actually makes sense. If we go back and look here, if t is 0 right here, then we're just getting our initial point, so we're not getting the backwards direction. So in this, I'll go ahead and go back here and switch this to, say, -4, and try that, and then we see that our tangent line is going forwards and backwards. Obviously, if I zoom out enough, it will kind of just be that section, but I can change my t-values if I wanted that to extend at all. Note, if I hold the shift key down, I can kind of relocate where this graph is on the screen here. Okay, and I believe that is all we are trying to do here. So use technology to graph the space curve and tangent line at this point. As long as I am talking about this, let's just note that we can label everything in different ways. If I click on this, we can go to settings, and we are able to put in a caption if we want. We can show a label, decide if we just want to give it its name, which would show a t, or name and value, or the value is just going to show the vector. I'm going to just plug that in there, so I see that that's giving us that vector. I can do something similar, click settings, let's show its value. Oh, I want a here, okay. So it was still on the t vector here, so I get that, and I'm going to switch that to value also. You have to exit out, you can't just click out of the screen. And then here I'll go to settings again, and I'm okay with just showing its name for this one. If you want a caption, if you're familiar with LaTeX at all, you can actually put in code. So I could say t sub and I'm doing a boldface for the R to show that it's actually a vector of 1, and I can do caption here and close that, and then we see that it actually does it in the nice tech code font here. Yeah, so that is that problem. All right. So now we're going to give you guys an exercise again. So go ahead and pause the video, and I will wait a few seconds, and then I'm going to write out the solution. Again, you'll see that just pop up in just a few seconds, and I'll kind of talk it through, and we'll just click this link so that you can confirm that you've done some good work. All right, go right ahead. Okay, so here's the work for finding the equation of the tangent line. We'll pull up the graph here in just a second. At the point 0, 0, 0, we can see from observation if we plug in 0 for t, then we get 0, 0, 0. And so we take the derivative of this. This is a little tricky. We've got to use a product rule here. So the derivative of the first is 1 times the second gives us sine of t, plus the first t times the derivative of the second, sine of t gives us cosine of t. Cosine of t. Then the derivative of t squared is 2t. And then we need to use a product rule and chain rule here. So the derivative of the first is 1 times the second gives me cosine of 2t. And then plus the first times the derivative of the second. But the derivative of cosine is negative sine, so I get a minus sine of 2t, times the derivative of the inside is 2 that I've put out here. So that's just a quick reminder of your product chain rule together. Make sure that you can pause and go back over that and that you can do that rather quickly. So I can then take the derivative at 0. So plug 0 in for t, and we should get 0, 0, 1. So my tangent line is 0, 0, 0 plus t times 0, 0, 1, or simplified as 0, 0, t. Whew. Okay, so we can click on this link, and when we do that, we should get this graph to confirm. We have our curve in here, we have our point, we have the direction vector, and we have the tangent line function in here. So I can kind of zoom around. I'm going to move this out of the way so I can see this a little bit better. And so here's our space curve at the point 0, 0, 0. We see that we actually have vertical movement. So it's just that vertical line is the equation of our tangent line in this case. All right. And we get to move on to unit tangent vectors. All right, since we've got a lot of the basics out of the way now, I think things are going to speed up for us a little bit more. So here we're going to try and do this pretty quick. I just want to find the unit tangent vector, t of t, we're going to call it. And this is actually a vector function that we're going to find, and then we're going to plug in and find it at the specific location when t equals pi over 4. So the difference between what we've done so far and what we're doing here is, well, here we are not going to do the tangent line at all. We're just going to look at the unit tangent vector, compare that to the tangent vector at this location. And the unit tangent vector is simply a vector in the same direction as the tangent vector, except for shrink down or expanded, stretched in some way in order to be a length of 1. So the definition here, the unit tangent vector is a vector t of t equals the derivative, as we've been doing, divided by the length of the derivative. And we can plug in specific t values to get specific unit vectors at different locations. So it'll be kind of cool when we look at the graph here. So before we do the graph, let's just work this out. So we want the derivative, r prime of t, and I'll leave this in our ijk component form. So the derivative of 2 sine of t is 2 cosine of t in the I direction. The derivative of 2 cosine of t is minus 2 sine of t in the j direction, and the derivative of tangent is secant squared in the k direction. And so this is our derivative function. We could then divide this by the magnitude of the derivative. So the magnitude of the derivative, my little arrow here, is the square root of the component squared. So we're going to try and simplify this a little bit. So this squared is 4 cosine squared of t plus square this, I get 4 sine squared of t plus secant to the 4th of t. I like putting a little tail on this just to say that's the end of my square root. Here we can factor out the 4. Sorry for the quiet here, just getting this written. We have that. And then I use, this is my Pythagorean identity for cosine and sine, so this gives me a value of 1 right here. So this just gives me 4 plus secant to the 4th. Like so. So our general tangent vector function equals our original function. Oh, I'm sorry, back that up, my derivative function over the magnitude of my derivative. So my derivative function here is 2 cosine, come on, oh, my finger keeps bumping the button, cosine of t in the I direction minus 2 sine of t in the j direction plus secant squared of t in the k direction all over this square root. And keep in mind that this square root gets divided into each of the components, just as we would with any addition in a numerator. Like if I had 4 plus 6 over 2, that this equals 4 over 2 plus 6 over 2, right? So this same idea is applied here, where the 2 cosine of t gets divided by this square root, the negative 2 sine of t does, and so does the secant squared. Okay, get rid of this. And so we want to know what is the tangent vector at this time value of pi over 4. So I can just plug in pi over 4 and work this out. So cosine of pi over 4, let's get our unit circle up here again. Here we have pi over 4 is at this location. And so this is root 2 over 2 comma root 2 over 2. So this is my cosine and my sine value. And so we have 2 times root 2 over 2 is the square root of 2. Can I move this down? I'm going to sneak this in here. Then minus 2 times the sine value is minus square root of 2j. Secant is 1 over the cosine value. So 1 over the square root of 2 over 2 equals 2 over the square root of 2 equals, if I rationalize this, then we get 2 root 2 over 2 equals the square root of 2. So that's my secant value. So secant squared is just 2. So plus 2k. And then all of this divided by 4 plus, so secant squared is 2, secant to the 4th is 2 squared is 4. And so this is the square root of 8. Square root of 8 equals 2 root 2. So if I divide all of these by 2 root 2, I get 1/2. So I get 1/2 I minus 1/2 j plus 2 over 2 root 2 is 1 over the square root of 2, and 1 over the square root of 2 is going to be root 2 over 2 in the k direction. Okay, so we're going to take this and we're going to check that our work looks good, that this is my tangent, my unit tangent vector. How do I know that it's a unit vector as well? I could say, is the length of this vector equal to 1? So if I took the square root of each of the components squared, 1/4 plus 1/4 plus 2/4, this does in fact equal the square root of 4 over 4 equals 1. So we see that the length of this tangent vector is 1. So that makes it a unit tangent vector. Let's go ahead and take a look at our graph here. Oh, where to go? There we go. So we have our curve. We have the derivative at pi over 4. And then I've got the derivative at pi over 4 divided by its own length gives us 1/2, negative 1/2, and then this hopefully should be the square root of 2 over 2. Let's just, in Google, square root of 2 divided by 2 is 0.71, one rounded. And so we can say, okay, our point is a of pi over 4, that's our starting location, and then this is the vector from a to a plus c, so this vector has a length of 1, like so. Okay. Let's go ahead and give you guys some practice. So same thing, go ahead and pause this video. and try this on your own first. And then I will wait a few seconds and go ahead and pause the video and write out the solution for you. All right, so gonna run through this rather quickly. Okay, running through this, we see if we take the derivative, we should get 2 cosine of 2t in the I direction plus 2 in the j direction minus sine of t in the k direction. The derivative's magnitude is the square root of these components squared. This doesn't simplify at all, so I wasn't able to factor out a cosine squared plus sine squared to make equal to 1 in this case. Our unit tangent vector function is the derivative over the magnitude of the derivative. If we just plug them in, we get this. This doesn't simplify at all here, but if we plug in pi over 2 for our t value as we were asked to in the problem, this actually simplifies down quite nicely to negative 2/3 plus 2/3 minus 1/3 in the I, j, and k directions, respectively. I am having a little bit of trouble with this link at the moment, so I've recreated the graph here. If you want, you can use this link to pull it up. I will fix that in the file later. And so here, I've put in my curve. I've then defined the unit tangent vector curve as r prime of t over r prime of t with respect to t from negative 2 pi to 3 pi, which is the same interval that I had for my initial curve up here. I then created a slider for my a value. I want to be able to slide this around. I'm going to do that in just a second. So I can plug in and find the unit tangent vectors at different locations and have them kind of move along this curve. So my unit tangent vector then is going to be, if a is pi over 2, we have the point r of pi over 2. Gives me that point a right here, r of a. And then we want the vector from that point to in the direction of the unit tangent vector function at pi over 2. So we plug that in, we get that same thing, negative 2/3, positive 2/3, negative 1/3 in our x, y, and z directions, or I, j, and k directions. And what I've done by creating this slider is I can now see how the length of the tangent vector is always 1. It's not changing, but it's always just pointing in the direction that the curve is going at any point as I slide that a value along. All right, so that's just kind of a nice thing to show what this tangent vector curve or function is doing. Is it's always outputting the vector that points in the direction of the curve from any point there. Okay. Moving along here, we are now going to find the tangent vector and unit tangent vector to the curve with this parametric form, these parametric equations. X equals cosine of t, y equals sine of t, and z equals t at the point 1, 0, 0. Real quick, I like stopping in the middle of a problem and being like, okay, I have this point on these parametric equations. What is the t value? So if we want z equal to t, then that shows me right away that t equals 0. And then I want to determine the parametric equations for the tangent line at this point. And we're going to use technology to plot the space curve, tangent vector, unit tangent vector, and the tangent line. So we're going to kind of see some of the stuff that I just did before. Just kind of one more time, walk you through all of it. So first let's note that parametric equations are the same thing as vector equations, where I could rewrite this as r of t equals cosine of t, sine of t, and there I go, getting my pen in the wrong orientation again, and t. Like so. And so I can go through and do the same kind of things where I can get the tangent vector equation, the unit tangent vector equation, and then I can plug in this t value to find the tangent vector at that point, the unit tangent vector at that point, and then we can come up with the tangent line also. So let's run through this. I need to get the derivative. Generally speaking, is negative sine of t, cosine of t, 1. And this is my tangent vector function. My unit tangent vector function is this divided by its magnitude. So the tangent vector, unit tangent vector function is the derivative divided by its magnitude, and I get the magnitude by just taking the square root of the square of the components using Pythagorean theorem. So I get sine squared cosine plus cosine squared of t and plus 1. And this is 1 right here. So this simplifies down to the square root of 2. I can rewrite this now as negative square root of 2 over 2 sine of t. I'm going to move this down to the next line. Negative square root of 2 over 2 sine of t. And I get this by rationalizing. Pause video and double check that real quick if you would like to. Square root of 2 over 2 cosine of t, comma, square root of 2 over 2. All right. And so then my tangent line equation we can get in a couple of different ways. So, okay, now I've got a notational thing where I've been using t of t here for the unit tangent vector function, and now I want an equation for my tangent line and have a notation for that. So I think what I'm going to do is put these little bars and use this and say, okay, we want this at t equals 0, so at r of 0. And this is the function for my tangent line now. And this has an input of t. So this has r of 0 plus t times r prime of 0. R of 0, if we plug in, we get 1, 0, 0. R prime of 0, we get 0, 1, 1. Which simplifies down to 1 t t. Okay, so we then want to do this all in GeoGebra. So if I scroll down to the next page, we have all of these nice instructions. It's going to kind of run us through. We're going to plot this curve. We're going to get our t values from one value to another, kind of get that all set up. Here we're going to create a point 1, 0, 0, and then we want to input a prime of 0. This a that it's referring to is what happens if I just type this into GeoGebra. Let's take a look at this real quick. So if I'm in GeoGebra, I can enter cosine of t, sine of t, t, and just hit enter. And what happens is it automatically uses a as its name if I haven't gone through this. So I don't have to type all of this out. It's going to automatically put in some of these things that I'd been typing out explicitly as I was going before. So the next thing the instructions tell us to do is to put the point in, the point 1, 0, 0. So I have in this input box 1, 0, 0. It's going to automatically name it capital A. It likes capital letters for our points. Then the instructions say input a prime of 0 since t is 0 where the point 1, 0, 0 occurs. Okay, so a prime of 0, and that gives us the direction, and it's written it as a point. We'll edit this in just a second. Let's note there were some instructions up here I skipped. It said have a starting t value of negative 2 pi. So let's just click in here, edit that. allows us to see the curve down in the bottom half there. So what we really want is we want the tangent vector at A, so I'm going to type in vector of A plus B, and this gets us the vector from the point A in the direction of B from A, doing A plus B here. And so that's what the instructions right here in the middle are saying to do, so that GeoGebra plots the vector from the point A in the direction of 0, 1, 1. If we want to plot the unit tangent vector, we're going to create a new vector, c equals b over the magnitude of b, to generate this unit tangent vector, and then put in that vector on the screen by doing this. So I'm going to create c equals b divided by the magnitude of b. We can just use the vertical bar on the keyboard to get that. And then we want the vector from a to a plus c. Zoom in here so we can see u and v. U is our long one, v is the one that's in the same direction but shorter because it's been normalized. Normalized meaning it's been stretched or shrunk to be a length of 1. Normalized in that context means to stretch or shrink down to a length of 1 while keeping the same direction. Okay, so now we have our tangent vector at the point A, our unit tangent vector at the point A. Then we want to plot the tangent line. So here we've used this nice little form here, x equals a plus t times c. So I'm using c, which is the unit tangent vector direction. I could also use b, but by using c it just means that since c is a unit tangent vector, t being 1 is going to take us in a direction of 1 from there. So I can just plug in x equals a plus t times c, and we get our line. C being a unit vector, what I mean by that is, say I have another point D equals f of create A. Why is this not showing me what's going on here? Let's try X. Yeah, here we go. So it wants a slider. Oh, what happened was A is already defined. I need to use a different letter here. So X, or D equals X of B. And we can create a slider for B. It wanted us to call it with F, not X. Sometimes that's a little confusing, but just look and try them both sometimes and see which one's working better for you. So now I have the point D on here, and so I can slide along. And what I mean by using the unit vector here for this is that if I move from B as 0 to get, let's see if I can see it, there's D right there, to B is 1, we have moved exactly 1 unit length along my tangent line. And if I move to B is 2, then we have moved another single unit length along that tangent line by doing that. If we would have used this tangent vector, then for every single unit of B here, we would be moving by that length. Okay, so here's the instructions again, and you can click on this link to confirm your graph is matching up with everything. And then I'm just going to scroll down here and go to our next problem. So now we want to look at angles of intersection. So I've actually put the graph into the picture here so we can see that what we want to do is, if I have these two curves, I want to know where do they intersect, and then I want to find their angle of intersection. So I've plotted them in Geogebra so we can kind of see what the whole purpose is they're both plotted right here, we can see that they do intersect. We're going to find that point, and we can say, okay, if they're intersecting here, then this curve's going in this direction, this one's going in this direction. At that specific instance, what is the angle between those curves? So we're going to go through and determine all of that now. So first, if I want to find out if they intersect, where they intersect, if they do, is if they're going to intersect, that means that the x values must be the same, the y values must be the same, and the z values must be the same. This is a little annoying that the text format bumped this over to the next line, but hopefully you can see that our y value is s minus 2 on our second space curve. So my x values matching gives me t, and 3 minus s must be the same, so t must equal 3 minus s for them to intersect. We also must have 1 minus t equaling s minus 2 for the y values to match. And lastly, we would need 3 plus t squared equaling s squared over here. Note that we have different variables here because the time for R1 may not necessarily match up with the time for R2. So we have a different variable that's governing the time, the movement along the space curve for this vector valued function. Okay, so if the x values are to match, t must equal 3 minus s. And so we're going to substitute this over into t here. And this is general practice. If we're ever looking for intersections of lines, then in some manner or another, we need to substitute them into each other. So here we get the different equations, my system of equations here, and then I'm going to start substituting them into each other. So if I take this and plug it in for the t over there, I get 1 minus 3 minus s. Make sure and get those parentheses so that that minus distributes to this. And so we have 1 minus 3 is negative 2 plus s equals s minus 2. Okay, so here we have a tautology. These are always equal no matter what s is. So let's, instead of doing this, let's plug this in over here. So 3 minus s into this. The reason I'm saying that is this isn't going to give us information about what s or t need to be, because these two, the x and y's, it looks like always match because of this tautology. So I want to see, how do the x's and z's match? Is that only at a specific t value? So I plug it in here, I get 3 plus 9 minus 6s, make sure and FOIL this correctly, plus s squared equals s squared. Here I get something, the s squareds cancel, and then I have 12 minus 6s equals 0. And I'll add the 6s, 12 equals 6s, so s equals 2. So if s is 2, I can plug that back in here and get t equals 3 minus 2 equals 1. So if t is 1 and s is 2, what's happening in these two space curves? First, the first space curve, when t is 1, equals 1, 0, and then plugging in 1 here, we get 4. We just want to confirm that, okay, these two, according to this work, should give us that the x and the z match, but does it also get the y to match? And it should because of this tautology here, but we're just double checking everything, making sure we haven't made a mistake at all. So the second space curve, we are plugging in the s value of 2 because s is the input value. So if I plug in 2 here, I got 1 for the x. If I plug in 2 here, 2 minus 2 is 0 again, and then 2 squared is 4. So yes, when t is 1 and s is 2, then both of these curves are at the point 1, 0, 4. How I like to think of the fact that t is different than s is that these intersect but at different points in time. So at 1 second after our starting time of 0, then the first space curve is at this point, and at 2 seconds after the starting timer, 1 second later, this is. So they're not colliding, they're not hitting that same point at the same time, but they are passing through the same location. Okay, so if these both go through the same point, we want to know what is the direction of each of the curves at these points, right? So I want to find their angle of intersection, but to know the angle of intersection, I need to know what is the direction of each curve at this point. So to get the direction, we need the derivatives. So the derivative of R1 is 1, -1, 2t, and the derivative of the first space curve when t is 1 is 1, -1, 2. Now our second space curve's derivative is -1. Oops, this is with respect to s, not t. -1, 1, and 2s. And if we look for what is its direction when s is 2, then we get -1, 1, 4. So the direction of the first space curve at 1, 0, 4 is 1, -1, 2. The direction of our second space curve at s is 2 is -1, 1, 4. So they're going different directions at the same point. I'm going to pull up that graph real quick. I want to try and show you guys visually what all we've found so far. Okay, so if I switch over, if I click on the link at the bottom of the page, we should get this pulled up. So we have the two space curve. We can see that they are at this location. Let me pull this back out. Oops, there we go. I want to show that point, show its value. You see, there's the point of intersection at 1, 0, 4, and then we have the direction vectors for both of the two space curves are going in these two different directions. Here, Geogebra has actually found this angle for us. We have the vectors themselves, and then we can just type in angle from those two vectors, and it spits it out for us. But we want to do that by hand. So let's switch back over to our page. And if we want to find the angle between two vectors, we need to remember the following dot product identity. So we have the cosine of an angle between two vectors. So theta is the angle between two vectors that we're looking at, is going to equal the dot product of the two vectors in question. Sorry, these are vectors, over their magnitudes multiplied together. So if you go back and review from chapter 9, we have this formula for dot products of vectors. And I can now use this where the vectors a and b are now the 1, -1, 2 and the -1, 1, 4. So if I plug that in, I get cosine of the angle between these two direction vectors. I have 1, -1, 2 dotted with -1, 1, 4. Over the magnitude of this, the square root of 1 plus 1 plus 4 times the square root of 1 plus 1 plus 16. So this, scroll down a little bit. The dot product, we multiply the components and then add them up. So 1 times -1 is -1, -1 times 1 is -1, and 2 times 4 is a plus 8. On the bottom, we have the square root of 6 times the square root of 18. So this is 6 over I'm just going to rearrange these. If I have 6 times 18, this equals 2 times 3 times 2 times 3 times 3, or 4. Put this in the following order. I'm going to write this as 3 times 4 times 9. So this is the square root of 3 times 4 times 9, which is 6 over 2 times 3, square root of 3, equals 1 over the square root of 3, and if I rationalize, that is the square root of 3 over 3. Okay, but that's not our answer. We want the angle, so we now need to take the cosine inverse of this. The exact value is the cosine inverse of the square root of 3 over 3. Which, if you plug this into a calculator, is approximately 54.74 degrees, as we saw that Geogebra had spit out. All right, that is our process for doing all of this. So to do this problem, we want to start by reviewing how to take the cross product. So if I have, generally speaking, 2 vectors, such as this, let's call them A and B. Then we can calculate the cross product by using determinant. So the first entry right here is going to be the determinant of looking at the second and third components of the 2 vectors. So if I put in here A2, A3, B2, B3, oops, then the second component is going to be where we look at the determinant with these components here. So we skip the middle when we're doing the middle, and we need a negative for the middle determinant. So A1, A3, B1, B3. And then for the last one, we skip the last and we use the first 2 components of A and B. So A1, A2, B1, B2. And this means we need to remember how to take a determinant. So a determinant is given by, if I have, say, A, B, C, D, this determinant is calculated as A times D minus C times B. So A, D minus CB. And we're not going to talk about what a determinant is. It is really just a formula here. So we have this formula for these 3 different components that we can use. So now we need to do this in context of this specific situation here. So if I have U, oops, of T crossed with V of T, this is going to equal the determinant of, so for the first component, we want to skip the first components here. So I'm going to use the second components, 6t and t squared, and then e to the negative t and 1. For the middle component, we then ignore the middle components here. We need a negative when we're doing the middle component. We use 2t and t squared. And then we use e to the negative t and 1 again. And for the last component, we ignore the last components here, and we use the first 2 components of each of these. So we have 2t and 6t. And down here we have e to the negative t and e to the negative t. So now we take the determinant of each of these. Here I get 6t times 1 minus e to the negative t times t squared. So 6t minus, I'm going to write it in this order, t squared e to the negative t. Here, I'm going to put the negative on last, 2t minus, oops, that should be a minus t right here, 2t minus this, these two multiplied together, but the negative will switch them, so this will be t squared e to the negative t minus 2t. And then finally, here we have 2t e to the negative t minus 6t e to the negative t for a total of negative 4t e to the negative t. Great. And so the derivative of this we can then just take the derivative of these components individually, get 6, oh, we need a product rule here, so minus the derivative of the first is 2t times the derivative of the second is a negative, which will make this a plus. I'm just going to go ahead and erase here. 2t e to the negative t. Wait. Sorry about that. Let me back up. So, minus the derivative of the first 2t e to the negative t plus the first times the derivative of the second. It's going to make this a minus right here. And then my second component, we have something similar here as what we just did, so it'll be this same thing without that minus in front. And minus the derivative of 2t is minus 2. And then the last component, we need a product rule again. So this is going to give us the derivative of the first is negative 4 times the second. Oops. Plus the first times the derivative of the second. Like so. And we can go ahead and simplify that. Sorry about the space here. This up here took more than I meant for it to. So I'll distribute this and get 6 minus 2t e to the negative t plus t squared e to the negative t. And then the second component is 2t e to the negative t minus t squared e to the negative t minus 2 and negative 4 e to the negative t plus 4t e to the negative t. Okay, so make sure you're okay with all of that, and then I'll have you guys go ahead and try this next one. But on this one, we don't want to go ahead and do all of this where we take the cross product first. Instead, we want to use our formula up here. So instead, we can take the derivative of u and v individually, and then say that the derivative of the cross product equals, take and use this formula. So we take this derivative and cross it with v, and then take the derivative of v and cross it with u, and then add those together. We should come up with the same answer here, but I will give you guys a chance to do that and come back, pause the video, come back, and I will show you the answer. Okay, so things were a little haphazard a second ago, so I rearranged them a little bit here on the screen. I put the directions for how to take the cross product up a little bit higher. Here we have the cross product of u cross v, and here's the derivative of u cross v in this manner. So now I'll come down here and let's work out how to do it in the other direction. So we're going to find u prime and v prime, and we're going to then take the cross products here. So pen here, u prime of t is going to be 2I, I want to do this in component form as opposed to ijk notation, just to make things a little bit smaller here. So 2, 6, and 2t, and v prime is going to equal negative e to the negative t, negative e to the negative t, and 0. Okay, so if I want, let's do this in parts. If I have u prime cross v, let's write this out. We have 2, 6, 2t crossed with v of t is e to the negative t, e to the negative t, and 1. So with our determinants here, and we have, for the first one, we ignore the first component, so I have 6, 2t, and e to the negative t, and 1. Then a negative determinant in the middle, where we ignore the middle, so we have 2, 2t, e to the negative t, and 1. And for our last component, we ignore the last components, and we use a determinant of the first two components. So 2, 6, 6 there, e to the negative t, e to the negative t. And simplifying this down, we have 6 minus 2t e to the negative t, by doing 6 minus these two multiplied together. Here, I'll put the negative on in a second, so we do 2 minus these, but that switches them. So that's 2t e to the negative t minus 2. That's how I'm applying the minus right here. So I'm just doing these backwards, essentially. Instead of 2 times 1 minus e to the negative t times 2t, I do e to the negative t times 2t minus 2. And then last component here, we have 2 e to the negative t minus 6 e to the negative t, which will simplify to be minus 4 e to the negative t when we put the whole thing together. The next thing we want to do now is u crossed with v prime. So let's just write these out again. 2t, 6t, t squared, crossed with v prime is negative e to the negative t, negative e to the negative t, and 0. So our determinant for the first one is going to use the second and third components, and then the second and third components here. And I say that right, the first and third components here, and then finally we ignore the first components for the last, or we ignore the last components for the last component using the first and second. So 2t, 6t, negative e to the negative t, negative e to the negative t. And then this equals, that 0 minus this gives us a plus t squared e to the negative t. Switch these, so this would be 0 plus this, that gives us a minus t squared e to the negative t. Catch that? We have a double negative here, because we would subtract this, and then we have a third negative here to make it negative in the end. Then here we have minus 2t e to the negative t, and then minus minus makes a plus 6t e to the negative t. All right, so finally, we can add these two together. So the derivative of everything equals, using this formula, we're just going to add this to this. So here I have 6 minus 2t e to the negative t plus t squared e to the negative t. And then in the middle, no like terms here, so 2t e to the negative t minus 2 minus t squared e to the negative t. And then here we have like terms here makes a minus 4 e to the negative t, and like terms here gives us a plus 4t e to the negative t. And if we compare this to what we had above up here, then we do see that 6 minus 2t e to the negative t matches up here, and plus t squared e to the negative t matches up. 2t e to the negative t here, minus t squared e to the negative t minus 2. And here I wrote them in the opposite order, but same thing. And then the last component also matches. All right, and so we see the formula does in fact work, and we should kind of expect this. This is our standard product rule when we are looking at a product and we want its derivative. We do the derivative of the first times the second plus the first times the derivative of the second. So we would hope that this would work, and in fact we see that it does work, at least in this example. This is not a proof, but it does work in all cases. So we are free to do either method that we want. All right. Okay, so if we want to do integrals, the short of all of this is simply that to take the integral, we're going to take the antiderivative of each of the components individually, and that becomes our antiderivative for the vector valued function, and then we can evaluate from the endpoints to give us the integral from 0 to 1 over this vector valued function, over this space curve here. And we'll look at what this is used for in following sections. I do not want to get into it at this moment. I'm sure you feel a little overloaded from everything in this video already. So let's just look at this, and we need to do some review of some basic antiderivatives. So if I want to take the antiderivative of 4 over 1 plus t squared, I need to remember, where are we? Where's my thing? There we go. Okay, so I need to remember that the derivative of the arctangent, if we're doing with respect to t, then of t equals 1 over 1 plus t squared. Or we could say that the antiderivative of this is the arctangent function. So let me rewrite this. It's generally not proper to put an equal sign here when we have a period. We want to restart our thought process. So I'm going to rewrite this up here. Like so, and then I can say, okay, this is, if I have the 4, that's just a constant. So this is going to give me 4 arctangent of t in the j direction. I'll do the evaluation here at the end. Next, I want this antiderivative. So here, it's not a constant on top, so I can't just pull it in front. Here we want a substitution. What I'm recognizing is that the numerator is the derivative of the denominator. So if I look at this integral, oh, I need a dt right here also. That's important. All of this integrated with respect to time. Then here I'm going to let u equal 1 plus t squared. So du equals 2t dt. So we see that we can replace the 2t dt with du, and we'll replace this with a u. So this is the integral of 1 over u du, which equals the natural log of u in absolute values, plus some constant. We're not going to use the constant in our context since this is a definite integral going from 0 to 1. So here I will just put u back in as 1 plus t squared. I do not want to put the natural log of u here because these are not u values, these are t values. So I want to keep everything in context of t over in this part. So natural log of 1 plus t squared, and all of this we are now evaluating from 0 to 1. So if I plug in 1 here, I have the arctangent of 1 is, the arctangent is giving us the radians when we're inputting the slope. That is, if I put up here, the tangent of an angle gives us the slope. So the arctangent takes the input and thinks of it as a slope, and it says what is the angle in radians here. So if our slope is 1, then our angle is pi over 4. So this is 4 times pi over 4 in the j direction, plus, if I plug in 1 here, I get the natural log of 2 in the k direction. Oh, I need my k here. And then we're going to take this and we're going to subtract. If a slope is 0, my angle is 0, so we get 0 in the j direction plus the natural log of 1 in the k direction, and we'll remember that the natural log of 1, or the log base anything of 1, is 0, saying e to the what equals 1, and so our answer here should be 0. So in total, I get pi in the j direction, and then this is 0, so we have just plus natural log of 2 in the k direction. So this is all very computational here. We're just essentially using the integral rules that we have learned in previous calculus classes and applying them in this larger context to come up with this answer, and we'll look at applications later. So last problem, go ahead and try this on your own now. And here in a few seconds, I will have the solution popped up and run through it with you real quick. All right, let's see if you managed to pull this off. We have a lot going on here, so I switch over to my pointer. The first one's not bad. That's really the only kind of gimme, except for we have to remember that the antiderivative of secant squared is tangent. So we have tangent of t in the I direction. The second bit uses a substitution. So I've done my substitution work over here. If we want to look at this integral, then I can let u equal t squared plus 1, so du is 2t. Again, I'm noting that the inside of this, its derivative, is just a multiple of this, so substitution should work. This is different than down here, where these two things, there's nothing in this that's going to give a derivative that is this, or vice versa. So here we're going to have to use it by parts. But up here, since the derivative of t squared is a multiple of t, we can use our substitution here. So I do this, du equals 2t dt. I moved the 2 over to the other side, so t dt, which I see here, is 1/2 du. So this t dt gets replaced by 1/2 du. The t squared plus 1 gets replaced by u, and the third just stays right there. So I can then take the antiderivative of u cubed, which gives me a 1/2 times 1/4, gives me 1/8, and raise that up by 1. And then I'll plug in my t value or my expression for u back in here, t squared plus 1 in for u, and I get this as the antiderivative of this. I'm not putting a plus c right here because I'm going to actually do that at the end of this entire expression. So here I have this expression in the j direction, And then this is nice and complicated. We have the antiderivative of t squared times natural log of t with respect to time. We want to try a couple different things maybe. We might try that u equals t squared and dv equals natural log of t. One thing that I like to say when you're doing these problems is don't be afraid to try something. Do it on scratch paper. If it doesn't work and you're feeling like you're going in the wrong direction, throw it away, start over, try something new. Maybe don't throw it away, keep it there for your record so you know what you've already tried, but switch it up, try something different. So if you try u equals t squared and dv equals natural log of t, you'll realize that you can't take the antiderivative of the natural log of t. If you try a substitution, you're quickly going to see that it's not going to substitute in a nice way where everything's going to be replaced. So we really end up being pigeonholed into u being natural log of t and dv equaling t squared dt as our only options, because remember, all of this needs to be seen in u and dv together. So then I take the derivative here, du equals the derivative of natural log of t is 1 over t dt. The antiderivative here, I get v equals 1/3 t cubed. And so this whole antiderivative is u times v, 1/3 t cubed natural log of t minus v du, so minus 1/3, and then 1 over t times t cubed is t squared, and dt comes down right here. And now I can take this antiderivative, so that's going to bump up to a 3, which I also divide by to give me a 1/9 t cubed. Again, the plus c I'm not going to put right here. I take this as this antiderivative and plug it in right here for my k direction. And then generally, as I'm taking the integral of all of this, we have plus some constant vector off to the side since this is an indefinite integral. And that's it. That is our section 2.6, or I'm sorry, this is our lesson 2 on derivatives and integrals of vector functions. And this is a nice introduction. We're going to get into some applications of this in the next lesson. All right. Thank you so much for listening, and I hope that you have a great day.